Hello there. Thank you for stopping by my poster. I am Aakriti Jain from University of Delhi, New Delhi, India, and the work I am presenting here is an interpretable machine learning based method for prediction of antibiotic resistance profile, and this case study has been done for Pseudomonas aeruginosa. World Health Organization has classified Pseudomonas aeruginosa as a priority 1 pathogen, and the hazard by this pathogen intensifies further as due to the development of resistance in this pathogen. And as we know, antimicrobial resistance or AMR has become a global hazard next to deadly diseases in causing fatalities worldwide. Bacterial AMR has been thought responsible for a total of 1.27 million deaths, and 80% out of these deaths are due to six major pathogens abbreviated as the escape pathogens. And Pseudomonas aeruginosa, being one of them, is a cause of serious concern. In this case, clinical decision making by the clinician is totally dependent on identification of the resistance profile of the bacteria. In the time taken for this identification, the ultimate choice is to depend on broad spectrum antibiotics and therefore increasing the load of bacteria further and increasing resistance further. So traditionally this time is 36 to 72 hours, the susceptibility testing. An alternative to this, the molecular based methods PCR are quick undoubtedly, but they are not very specific and they are dependent on already or previously known resistance markers. So in this scenario, machine learning or artificial intelligence can act as a boon or offer solutions if they are supplemented with genomics based diagnostics, and then they can be a promising alternative or they can be used in clinical scenarios. The turnout around time can has proved to be good. Also specificity, but a major strength of these methods can be identification of unknown resistance mechanisms. So in this study, we've developed a two-tier machine learning model for Pseudomonas aeruginosa, which in the first tier detects whether the strain is resistant or susceptible, and the second identifies the specific antibiotic against which resistance is known. We've also worked on the interpretability of the model using explainable AI through Python, and here the input of the machine learning model we have encoded as k-mers, which are fragments of the genome. So we started with data processing and collection. We collected data from Patrick database, Pathogen Resource Center. So using different criteria, we filtered and curated the data set, and finally we had so and so resistant and susceptible data sets for tier 1 of our model, and for tier 2 we segregated the data as susceptible and resistant to a particular antibiotic as shown here. So then we moved on to build our model. We had resistant and susceptible genomes. We chopped off these genomes into k-mers, and K here stands for different lengths of nucleotides, that is 5, 8, 13. We had segregation like this up till 32. And then we went on to build matrices of k-mer presence and absence in particular genome, and we had two sets of these k-mers as in for resistant and susceptible data sets. We went on to filter the k-mers based on their quality and frequency in the data sets, and then we built matrices for distance calculation, and we selected the k-mers and finally went on to associate the k-mers with the phenotype using statistical testing. We used both parametric and non-parametric statistical tests, Wilson test, t-test and others, and we associated the k-mers to the phenotype. Phenotype here is resistant or susceptible. Finally, the features of our model were encoded, that is, the input data is the genome, and we encoded it as k-mers. Went on to build the model using SVM or RF, different machine learning algorithms like SVM, random forest, or decision tree. We used all the we use the common types of machine learning algorithms, as in to analyze that which kind of algorithm fits best for the data set we have at hand and the problem we are trying to encounter. So after modeling, we went on to prediction and validation of our model with an independent data set from NCBI. This data set was not used in building the model. Finally, we inferred from us, for then we obtained various parameters for our model, different models, and we found out that the Kamer length 13 and decision tree models worked best for us. And we also assessed that mere accuracy is not a parameter to analyze whether a model can be clinically used or not. The application of a model or the efficiency of a model is cannot be completely judged by mean accuracy. We went on to weigh uh, both all kinds of parameters, both threshold dependent and independent parameters like MCC value and ROC values, and through those we understood that decision tree models worked best for this kind of resistance detection data for Pseudomonas aeruginosa. We had the accuracy achieved for decision tree is 0.85, 85%, but the specificity and sensitivity were comparatively good. Then we went on to interpret our the models using Shapley additive explanations. SHAP, it's a Python package of explainable AI. In this graph here, you could see the pink color indicates high or high impact, and the blue indicates low impact. On the here middle is the 0, on the right side is the positive sharp values, left side negative sharp values. Positive values indicate our the one of our machine learning model, that is the resistant, and negative values they indicate the other prediction, which is susceptible. So for a particular Kamer, as you could see, for this is blue, there's a blue bar and a pink bar. The blue bar is like it is near to the median line, that is around sharp values around 0.7. The pink is farther away, the sharp values around 1.5. So from this we can assess that the impact of this particular Kamer is higher on the resistant dataset but lower on the susceptible dataset. So through graphs like this, we could assess the impact of each Kamer or each feature on the prediction of our models, and we could pinpoint the Kamers which are playing a role in making the particular genome or particular strain of a Pseudomonas aeruginosa resistant. So finally, concluding my talk, we inferred that simple tree-based algorithms like decision tree can yield promising results if we assess all the model parameters subjectively, and we also move on to see all the features objectively. Then data is undoubtedly the backbone of any machine learning model, but also it's a critical parameter to assess that what kind of input or how we assess the available data. As in, if we went on to take just the genic or the functional regions, then the entire genomes are obviously not scanned, and therefore it can be limiting, especially in cases like Pseudomonas aeruginosa, where resistance is a result of horizontally transferable genetic elements, and therefore entire genome scans can offer a clinically dependable picture of resistance. So we conclude that genomic data should definitely be complemented with transcriptomic, proteomic, and metabolomic data. The interplay of threshold dependent parameters and independent parameters determines the performance of a model and not just accuracy. And comprehensive dataset making using k-mers can be a promising and efficient approach in such models for bacterial AMR. And finally, without enhancing model interpretability, the application of machine learning methods in resistance detection will be limited. Thank you very much for your kind listening, and I acknowledge my funders DST Serb India, UGC CSIR for my PhD fellowship, and AP Bionet for allowing me a fellowship to travel to this conference. And I would happy to have questions in the chat box, or please, I'll be happy to meet you any of you and connect in the conference. Thank you very much.